Hello and welcome to another episode of TypeScript Type Theory, simple types as a fragment of TypeScript types. In this episode, we'll define simple types using the TypeScript compiler. Now, this isn't possible for every type system because the TypeScript compiler itself implements a type system. But for simple types, because they are a fragment or a subsystem within the system used by TypeScript, we can actually define them using pure TypeScript types. So let's start by talking about the concept of church-style type theory. So a little history. In the beginning of the 20th century, Bertrand Russell was doing Principia Mathematica, and he was trying to avoid some of the set theoretic paradoxes. I have another video about Russell's paradox. And he introduced the concept of types to distinguish different types of sets from each other. This was the first attempt at a type theory, and Russell's type theory was very complicated. So later on, Frank Ramsey and others introduced what was called the simple theory of types. It was not necessarily that it's simple compared to other things that are not type theory, but it is simple compared to Bertrand Russell's type theory. And it's also simple compared to some of the more modern type theories like dependent type theory, which are also complex in a different way. But what we're going to mainly focus on the version of simple type theory created by Alonzo Church in the 1940s or 50s. And that was the first version of type theory that was really focused on computation, because Church, as you may know, introduced the lambda calculus from our first episode. So he kind of provided one of the main models of main mathematical models of computation. And it's still the basis of functional programming to this day. So here I've got raw base types, so I'm just using JavaScript types that aren't complex. So some of the primitive JavaScript types. You could add to this list, of course, but I'm just including numbers, booleans, and strings. This is just a way of kind of making it look more formal, because you're essentially just passing in that type argument data type, which extends the raw types, and it's returning itself. But this means that we can treat our simple types as always taking one type argument. We should look down here at the function type. So basically in Church's type system, there's only really one way of constructing new types from existing types, and that's to make a function type. So you may have seen in functional programming languages, or even in JavaScript, you have this kind of arrow syntax, A to B to C, right? And essentially that is defining the type of functions where you take in an input of type A and you go to a function of type B to C, which itself takes in an input of B, and so on. So really any combination of two types can be stuck together as the domain and the codomain of a function, or the input and output type of a function, and that gives you a function type. So that's the type of all functions that go from the domain type to the codomain type. And so then this was a bit out of order, but up here, the Church simple type is just those two things, the base type and the function type. Now, a little TypeScript note, I had struggled with defining these types, because if you try to put in, you might think, okay, I can put in the Church simple type here, but I immediately get a type error. And if you look at that type error, it says, this circularly references itself. So there might be a workaround for that, and if any of you know of one, please let me know in the comments. But for now, I've just used the any type as a way of kind of getting around that with these recursively defined types. Okay, so let's give an example, like to make this a little more concrete. We can say the type of a binary operation in our simple type system is like this. It's a function type that actually goes from a number and returns another function type, which also goes from a number to a number. And we can then concretely instantiate that with the add function. And so you can see here, we don't need to add any types to our arguments, because TypeScript will infer that X is a number and Y is a number, because we've assigned it this type of binary operation. And you can also see here that TypeScript just reduces this to the type of a function from a number to a number to a number. So that's a nice use of generics there to get that type inference. And then I've just created here a simple predicate. I don't really end up using this, but just to show you, if you want to determine whether a type is sort of inside your type system or if it falls outside of your type system, you can create a predicate, a type predicate, which takes in a type. So this is any type, it's unrestricted. And it uses a conditional type to say, if it does extend this type, then true, otherwise false. So we can test some specific types here. We can say, we can take the type of our add function here. And, well, that's the add2 function. We can also just do the regular add function. And we can see that it gives back true, that's from the compiler. And same thing with this version of it where we add 2. And same thing with our isEven predicate. So this has a type from number to Boolean. But remember, Boolean is also one of our base types. So a predicate like that is also a church simple type. But what about this one? So this is our third version of our add function. Here we take 2 arguments and we return the answer. So we don't return a function first. And if we check that, we can say, oh, it's false, right? Because we don't have any 2 argument functions in our simple type system. And so you'll notice that in languages, functional programming languages like Haskell, by default, when you pass arguments to functions or when you define functions with multiple arguments, they are what's called curried, which is just another way of saying that they only take 1 argument at a time and they keep returning functions where the arguments get applied 1 at a time, which is called partial application. So let's move on. Although you can actually do almost everything, like in logic or in programming, with just these church simple types, and this is one of the amazing things about Church's system, is just with function types and base types, you can essentially do everything you need to do, almost everything you need to do in logic, at least for basic logic and programming. But it's very convenient to think in terms of enriching the type system with some other pretty fundamental types. And so we're going to do that now. So one type, or like 2 kind of types that go hand in hand, are the singleton type. And we've just used a JavaScript symbol here since it's guaranteed to be unique. It's not just the string of that, it's the actual unique value. And then you can take the type of that unique symbol and assign that to the singleton type. And the empty type is just essentially a type alias for never, which is TypeScript's version of the empty type. And so these are useful in a category theory, which is closely related to type theory. This would be what's called the terminal object, and this would be what's called the initial object. And those turn out to be pretty useful theoretically. And when we get to a later episode where we're going to look at what's called the propositions as types interpretation of type theory, we'll use these in order to ensure that, like, if a proposition is true, it is capable of being instantiated as a singleton type, and otherwise it will get the empty type and not be capable of being instantiated. So the next type we're going to look at is called product. Now this is, we already have this in TypeScript as the tuple type. So if I just do type, I could do type pair equals any, or to get better type inference, I can just do AB and AB. And now that's also that is a product type. It's a form of product type where we just take the pair of A and B. But again, just to make it give it a little bit more structure and to differentiate it so that it's sort of internal to our type system, we can also make it an object type where there's these 2 properties. These are what are called the canonical projections, pi1 and pi2. When you see it written down, of course, it will be with the Greek letter pi, not pi. And these are basically, a product is defined as something that you can take a projection of. Namely, you can take one element or the other element. And it's also often thought of as an ordered pair. Although that's true when you're thinking of it in terms of programming and in terms of sets. But it's not always true if you're interpreting it in other categories, thinking of different kinds of mathematical objects that might have products. But leaving that aside, you can think of it as an ordered pair or as an object that has sort of 2 canonical getter functions or getter properties that will get you the first one or the second one. And then the next one is coproduct, which is also sometimes referred to as a either type. In Haskell, it's called the either type. And this one is basically like saying, well, this one says you're going to have like one value of type 1 and one value of type 2 in the order, in that order. This one is going to say you're going to either have a value of type 1 or a value of type 2. So before we actually define the coproduct type, we need to define these things called injections. So these are, again, just like here, we have canonical projections that take a product and split it up into its first and its second member. Here we're going to actually have a way of injecting values of type 1 and type 2 into our coproduct. What we're saying here is I have a type which extends simple type, and and this object is basically just saying that it's being injected into the first half, the first part of my coproduct. Or I have a type of another type and it's being injected into the second half of my coproduct. So then a coproduct for type 1 and type 2 is defined as the first injection and the second injection with type 1 and type 2 respectively. Notice we're using TypeScript's union operator. And one of the key things about the union operator, it doesn't always preserve the two sets you're unioning. So for example, if I let's just call this union, right? If I union the set of string A and the string B, right, then, that's fine. So because each of A and B are distinct, but if I union A and B, I'll put the brackets around them, and I union that with A and C, right, then what I get is the set containing A, B, and C. Okay, so that's with a union. With a coproduct, however, if I take the coproduct of, so if I do the same thing, take this as my first type, and I don't need the brackets because they're different type arguments, and A and C, then what do you think we're going to get? Well, we're going to get injection 1 of A and B unioned with injection 2 of A and C. And so this is not going to eliminate the duplicate A's. In fact, it ensures that these duplicate A's are going to be different from each other, because this is A occurring inside of injection 1. So the A is going to go there, and it will have this other property I1 that will ensure that the object is structurally different. And so the coproduct construction ensures that you have what's called a disjoint union. Disjoint means that even if you start with two sets that have some overlapping values, it will ensure that the resulting set, it doesn't collapse any of the values together. And it does that by wrapping them up in these two injections before unioning them. We're going to walk through an example of a coproduct type. We've created our variable disjoint union using a coproduct type that puts together the set A and B with the set A and C, just using string values here. So when we try to instantiate that, if we use I1 and A, no problem. Similarly, if we use I1 and B, no problem. Now if we scroll down, we try now using injection 2 for A, and that's also no problem because A is also in this set. But as soon as we try to instantiate it with B and I2, the TypeScript will correctly infer that B is not assignable to type AC. So what TypeScript has done is it's used the injection I2 to infer that this must be, the value must be of the type that comes from the second type argument in our coproduct type. And that's pretty great when you think about it. Now, if we go down here, we can of course see that if we put in C, that will work for I2. But if we were to change this to I1, we would also get an error for C, since C is not in the type of A or B. Here's just another example. You can take the disjoint union of string and number. The other thing about it is, though, it preserves the order of the injection here. So if I assign it to coproduct, I've assigned the type as coproduct string number, and here I've assigned it a valid value because I have I1 here, and TypeScript infers that because this is I1, it must have the value of a string. If I hover over here, it will tell me that it's a string, not that it's a string or number, right? If I go here and I try to use the I2 value here, TypeScript will infer that this should be a number, and it will tell me you can't do that. It's going to be some complicated error message, but it says it's not assignable to type because string is not assignable to number, right? And so similarly, if I were to go up here and change this to a number, it would give me a type error because the number is not assignable to I1. So that's pretty nice type inference you get there. And here it's just showing that this one works when you assign the number to I2. Okay, so that is essentially the conclusion of today's episode. To review, we can now define our simple type as a church simple type, which is a base type or a function with a codomain or domain. Do the church simple type, the singleton type, the empty type, the coproduct, and the product. And that together forms our system of simple types. Now, in the next episode, we'll be looking into propositional logic and using TypeScript actually to kind of create a propositional logic engine. And then in a future episode after that, we'll look back to these simple types and how we can use them and interpret them actually as being a form of logic in the type system itself. Thank you for listening. Please comment if you enjoyed this, if you have any questions, if you find any mistakes, or if you can see better ways of doing things. And and if you want to see more videos, you can subscribe to the channel. Okay, bye.